Yes. Anyone here? Okay. My talk is about is in the sense a little related with the previous one, and it's about using generative models to predict conformals for materials design. This is a project with two teams. From Inesctec, the work is being done by me and José Oliveira, and there's a team in University of Aveiro, which is the chemistry team that is working with us and gave us this problem to tackle. So the problem is about antimicrobial medical paper packing. So this is an application of generative models prediction. So the antimicrobial medical paper packing has several drawbacks that need to be tackled. First of all, you have sustainability constraints. So usually single-use medical paper packing usually uses non-biodegradable synthetic laminates, so which are not eco-friendly. There are also sterilization limitations. So biopolymers like thermoplastic starch usually exhibit very high hydrophilicity and poor resistance to sterilization, which compromise barrier and mechanical properties. So these are the first ones. Another drawback is antimicrobial deficiency. So usually we lack on biodegradable coatings, which are tailored with antimicrobial properties for medical use. And of course, they give higher risks of healthcare which are associated with infections. And finally, the solution which is ready to use are conventional trial error approaches, which are of course very slow and resource intensive. So the idea is to actually create thermoplastic starch coating, which will integrate porphyrins, which are light activated antimicrobial, which have light activated antimicrobial properties, and these porphyrins will be optimized through machine learning for ISU completeness and sustainability. So the idea is to use molecular conformer generation. As you all know, the 3D geometry of a molecule is usually known as a conformer. And of course, the 3D geometry is critical for determining K properties such as energy. And that's why nowadays, most of the conformer generation models use the 3D geometry as an input. So in the task associated with molecular conformer generation usually involves generating low energy equilibrium ground state geometries, having the 2D molecular graph as input, considering, of course, conditional tasks. It offers a faster alternative than computationally intensive methods like DFT, having, of course, an high potential to enhance molecular simulation efficiency. Okay, so what is the problem setup? We assume that each molecule with n atoms is represented as an indirected graph comprising a set of vertices, which are the nodes, representing the atoms defined by their element type, and a set of edges, which represent their interatomic bonds. We have associated the 3D geometry, which embeds each atom in a 3D coordinate vector, and having n atoms, we have a matrix with a dimension of n times 3, which is the coordinates of the atoms of the molecule. And of course, the objective is to generate stable conformations given the 2D molecule graph G, by using a generative model that will efficiently sample conformations approximating the Boltzmann distribution. Okay, what are the technical challenges associated with this task? First of all, reconstructing the 3D molecular geometries from the 2D graphs has to ensure that there is validity in the 3D space of the geometric conformer generated, preventing, for instance, atom overlap of the generated conformer. It also has to maintain the chemical validity of the conformer fragments. For instance, in the case of porphyrins, the aromatic ring has to be on the same plane. And of course, the geometry reconstruction must be invariant to simple Euclidean transformations, and we are talking about rotations and translations, which means that conformers rotated and translated are equivalent. So the proposal is to use Generative, which is a geometric diffusion model. It starts with a Gaussian standard conformer. We start with a given graph G, and the 3D structure is generated, first of all, sampling chaotic states which are obtained via the diffusion process, and then through an iterative process, which is the reverse process, which is learned from a neural network. The means of the normals that are that characterize the distributions of the atoms of the coordinates of the atoms are sampled in the reverse process. So this is a dual process. In the diffusion process, the conformers are diffused, starting with the conformer C0, and then diffusing the conformer having noise to come to the CT, and the reverse process starts with the CT, which is a standard Gaussian, and through an iterative process learned by the neural network, will reconstruct and denoise the conformation. Okay, so we started by extracting the porphyrin molecules from the PubChem compounds database. And actually, it was a very good extraction. About 48,000 porphyrins were available, but only about 9,000 of them had conformers, limited to 1 to 10. So as a starting point, we collect the SMILES representation of each molecule, for each molecule, and that conformation is available, and format them in as PyTorch geometric objects to be inputted in the model. And you have here on the scratch, you have the porphyrin ring, the simple one, with the chemical formula and the SMILES representation. Okay, what was the experimental setup? We assume that to have a reasonable training, we had to exclude molecules with a very few conformers. So we assume that all the molecules in the training should have at least 3 conformers. Then we use the data available divided it in a training, validation, and test set, using 80% for the training, which came up with about 48,000 molecules, and the validation set about 600. And we considered the test set with 200 molecules, having at least 5 conformers just to comply for the assessment to be reasonable to assess to the generated conformers. We trained the model for about 48 hours in a partition of a NVIDIA A100 GPUs from the Eucalion Euro HPC, using a batch size of 64 molecules, using a learning rate of 10 rises to -3 and an atom optimizer. The diffusion steps were 5,000 for the diffusion and reverse process. And for validation, we validate every 5,000 iterations with a patient of 10. And the variation levels for to be used in the diffusion process started with 10 rise to -7 and ended 2 times 10 rises to -3. So this is the result, the first results, because the data set is still very small and can be expanded. So on the left, on the first column, you have the 2D structure. On the center, on the center column, you have the reference set with the conformers available on the test set, and on the right, you have a conformer generated by the trained model. And as you see, the conformer, the generated conformer is in compliance with the symmetry of the reference set in accordance with the symmetry necessary. Okay, so to test the model, we use the usual metrics, which are the coverage and the matching. In the case of the coverage, it measures the proportion of conformers on the reference set which have at least one generated conformer in the test set, and the match between them is measured by the root mean square deviation. We use a threshold of 0.5 for that match. And to measure the quality, we use the matching, which calculates the average of the root mean square deviation between each reference conformer and its closest generated conformer. And on the table on green, you have the results that we got until now. So we have the matching values are still very high, although we don't have any comparison, because as far as I know, there are no porphyrin data sets which were used in this kind of applications. But comparing the results with other data sets, it's still a bit high, and the covariance is very low too. So what are the next steps? The next steps will be to enhance the porphyrin data set. We have to be able to calculate conformers for the other molecules and retrain the model again, and possibly to compare the results available with other generative models, such as variational autoencoders and the generative adversional networks. It would also be nice to compare the results gathered with applying transfer learning and a few-shot learning. So to train the model with a broader data set, and then make a few-shot learning with our smaller data set, and compare the results with the first ones. Of course, to close the research, we have to be able to predict the light activity antimicrobial properties of the candidate porphyrins. So on the second step, we have to be able to try to predict that using a prediction model. So concluding, we were able to successfully develop a diffusion model to generate 3D conformers for porphyrin molecules. The challenges associated with conformer generation accuracy were assessed using coverage and matching, but there are challenges that need to be tackled yet. But the potential of using machine learning to accelerate design of antimicrobial TPS-based coating is demonstrated, and we established a basis for future advancements that will be able to propose new molecules that are sustainable in terms of eco properties.
Thank you very much for the talk. Are there questions? Yes, Rambi.
Thank you very much for that really deep dive, clear description of the diffusion approach. I have two questions. One is why not train on non-porphyrin molecules as well? Because it will still understand the geometry. Although your application area is porphyrins, why not do that? That's one. The second question is, your input prompt is basically the graph, molecular or smile string or molecular graph, right?
Yes, the 2G and the conformation. So the 2G and the set of conformations.
Right. So, the set of conformations.
Yes.
Okay.
Yeah, he has to train with the conformation. So it will train with a molecule and each conformation that is available for that molecule.
Okay.
Yeah.
So
you will repeat the process for each molecule, for each conformation of each available for each molecule.
Right. So for a new case, It'll produce all the different conformations?
Yeah, the promising idea is to be able to acquire more conformations than the one that are available, and test those that maybe are better promising in terms of lower energy.
Okay. So my first question is, why not train on all the PubChem?
That's the one task.
Okay.
Yeah, so the idea is, why not use all the, well, you have to have resources for that, but why not use a broader database and then make transfer learning on the smaller? Yeah, that's maybe we don't know the answer, and it would be awesome to see if the result is the same or better or worse.
There's a question over there.
Thank you for the talk. You just touched energetics. Like, how do you judge the energetics? Do you just have like a standard computational chemistry workflow afterwards, or is there some score?
You have to give the energy also. The minimum energy is also given to the input. So when you transform the conform into the form that is understandable by the model using a geometric, using PyTorch geometric, that information is available for the input. So you have to give him the energy.
And then you also get an estimate for every new
Yes,
conformer.
yes, that's right.
How reliable is that?
Well, you have to go into the details of the chemistry. That I'm not the expert on chemistry, but as far as what I can tell you is that this is given by the model, and you have the model giving the energy as an output. So you can have each conformer as the minimum energy associated, and you can rank them based on the energy, and of course choose the one that has the lowest energy as the best candidate.
Yeah, thank you a lot.
Do we have other questions? I don't see any right now, so let's thank our speaker again.